I'm here to tell you probably a little bit about what mathematics is all about at university, what you do with it. So I'm a professor of pure mathematics at Royal Holloway, and I will tell you a little bit about sort of what mathematics generally involves at university, and that won't be so different from university to university. So since I'm at Royal Holloway, I know a little bit more about what's going on there, but in general, the first year will not be very different at any university, and what you do afterwards won't be that different either. So even though we have a slight bias here, it's a sort of a general thing of what's going on. So I guess I should start by asking you guys why you like mathematics, or what you want of it. And I don't know. Yeah. So why are you interested in mathematics? What do you think is exciting about it? Yeah?
Well, it always works, because it's like, in like science and stuff, you always end up with sort of experimental errors and sort of things that you can't account for. But in maths you can account for everything.
So if you can prove it, you know it's correct. I wouldn't say it always works, because you sometimes bang your head against a problem for years. But once you have it, you have it. That's true. That's a sort of very satisfying thing. You know, once you've got an answer, that's it.
It can be a really nice framework for nature. If you test it in maths, nature sort of works out. There's no framework for everything around us.
It describes what it is. It's a tool to describe things as well. Any other reasons why you sort of possibly are considering doing mathematics or something math-related? So you're just here to be curious, I guess. So yeah, so the thing is, so what I wanted to show you is a little bit about how you can use it, this sort of applied side of it, the sort of certainty of it, and also, I say, beauty of it. Mathematics can also be very beautiful, very satisfying. So, yeah. So if you're considering to do mathematics at university, so what I will talk about is mathematics and sort of some joint honors, mathematics with subjects. What I'm going to say is, what should you look out for? What is actually happening at university, because university mathematics is different from college or school mathematics. I guess you're all, what, year 11, 12, 13, around that? Yeah? So it's very different from school mathematics. And then I'll say a little bit about how to apply, but I think your teachers know that better than I do. So you come to us once you've done all the hard work. And, okay, so entry grades, they vary a lot, of course. So anybody who wants to do maths can possibly do mathematics somewhere. So they're Oxbridge, Cambridge, so you need 3 A's and an A star somewhere, and some step papers and an exam, and the step exam and an entrance interview. And then there are places like Russell Group, Royal Holloway, places like that, who ask for around triple A's to AB. And so we have degrees, maths degrees that ask for AAA. We have others that ask for a little less. And then there are smaller places, ask for smaller things in there. We will probably do some more applied things. But I'm going to talk about sort of the university, sort of what sort of Royal Holloway equivalent universities would do. Yeah. So yeah, that's where I'm from. That's where I work. Nice, isn't it? It used to be a women's college. So coming to a boys' grammar school is quite funny. So, and it was founded as a women's college more than 100 years ago, 120 years ago, and became part of the University of London about 100 years ago, and started taking men 50 years ago. So it's got a long tradition. So it's a lovely place out somewhere in Surrey, the other end of Surrey, but also close enough to London to defend. Probably not too different from somewhere around here, except that we have a castle. So, but once you think think about where to go, what to do, you should ask yourself, what do I want from my course? Yeah? Which courses should I take? So the thing is, do you want to do just mathematics? Do you like your maths modules? Do you like if you do further maths modules, do you like them? Do you want to go on further pure? Do you want to go on and do a bit more like that? Things like that. Or do you want to sort of think, oh, okay, I'm also interested in economics, I'm interested in other things. So you should think very carefully, what do you want of a maths degree? Yeah? So, and then you should go and see what's there, what's out there. And then if you go and visit places, you should say, can I see myself there? Can I see myself walking along these corridors or walking along the campus? Can I imagine this as a place I want to be? So I think that's very important things. You should more or less know what you want. You will not know. You will probably change your mind in your first year about what you enjoy. But sort of you will have some kind of idea. Try to see that first and also once you. But once you are at university, once you do something maths related, you learn a lot. And you don't just learn mathematics, you learn all these things like how to formulate a problem. You'll be very good at saying, somebody asks you something and you will learn how to put this into concise words, explaining it well. If you have some process you will have to describe. In mathematics, you learn how to build a logical argument. You're not going to write a novel when you write something for somebody else if they want to follow what you've been, so the process you've been describing. So yeah, personal organization. You won't have parents telling you, do your homework. You have some lecturers breathing down your neck, but that's it. So you have to learn how to organize yourselves. And a maths degree is quite structured. You have to keep on doing exercises and weekly worksheets and things like that. Because mathematics, as you know, you just don't learn it by watching. You have to do it. So that's probably for many other sort of sciencey degrees, engineering type degrees. But most of all, yeah, you learn how to read mathematics. You learn the language of mathematics. You learn to read this equation here, e to the I pi plus 1 is equal to 0. You learn probably also to appreciate things, the beauty of things. What's beautiful about this one? Look at it. We've got the Euler number here, which is irrational. The pi, which is irrational. I is the complex, root minus 1. So you have this expression here, which looks really outlandish. And then you add 1 and you get 0. Now why should this expression be minus 1? And you learn to appreciate things like that, so those little oddities that intuition tells you cannot possibly be. Why should that be an integer? I don't know. You don't know if you just look at it. So let me tell you a little bit about degree programs. Again, I will tell you about what we offer, but most other universities will probably offer very similar programs. So there's a BSc in mathematics as a standard one. If you really enjoy your maths A-level and you want to do more, you want to understand, for example, why calculus works, or why using matrices and what they do for us, then that's it. Or if you're really super duper excited, you do a 4-year course, you do an MSci or M-Maths in some places. If you're more into the statistics side of it, or later the applications of it, statistical applications, you can do maths or statistics. And some places, including us, offer a degree called mathematical studies, or maths with applications, or mathematical modeling, which are more sort of focused onto the applications, and also gives you a little bit more space to go elsewhere. It's not that it's not as rigorous a maths, but it has a very substantial maths component. And then, of course, there are the joys. These are those. Then there's things 50-50 programs, and then there are programs where you're actually interested in something else, but you think I should gain some more math skills. So these are the 75% maths programs. So you can do languages, you can do management or finance or philosophy. Then there are joint programs, computer science, economics, finance, management again. Music is a very popular one, surprisingly, not surprisingly, I guess. Physics, of course. And then here's also a 4-year program in maths and physics. So this is, and students who take that, what they often do is they take the more applied theoretical physics courses in the maths degree to go with the physics. So what they will gain is a very sort of theoretical physics. And what else can we do? And then there are things where you just have a little bit of mathematics. You want to learn a language, but you think, I also think I want to know more maths. Or I want to go into business, but I want to be a numerate business person. And maths becomes maths. And again, so there are other combinations that are not on this list. Have a look when you look at stuff. And then, if you haven't had enough after 3 years or 4 years, you can do MSc courses. And there you can specialize. Again, I'm only writing out the ones we are offering. You have to look around. There are many, many applied type mathematics MScs. There are maths for applications. There's straight mathematics MScs. For example, Cambridge offer something they call Part 3, which is an MSc, just in mathematics. We offer something with cryptography, which is sort of based on our history. So we have a very strong information security group, economics, stats, information security there. But there are many others, maths with finance, maths with actuaries, whatever. There are very, very many masters out there. And of course, you can do a PhD. If you think, what, after 3 years, 4 years, I want to do more maths, I haven't had enough, you still haven't had enough, then you do a PhD, and you do research. That's your chance to do something in mathematics. So I guess that's what I went, the road I went down. Can we get enough? Okay. So let me say a little bit about the BSc in maths, what you do. Mathematics, you need foundations. You can't start a little bit here, a little bit there, and then a little bit. What you need are your foundations. Therefore, the first year, in almost all places you go, is fixed. You have no choice. And that's not because we are mean or anything, it's because that's what you need to know. You need to know your linear algebra, vectors, matrices, and further on. You need to know your calculus, and differential equations, we are the calculus. You need to know calculus not just of one variable, but several variables. You need to be able to work with it. And you need to know why calculus works. I guess, have you all seen derivatives? Yeah? So when you do x derivative of x squared, why is this 2x? You've probably seen this. Yeah? So your approximation process. You take the slope on your curve, but you can't. The tangent, how do you find the slope of the tangent? You can go slow and slow and slow, the h becomes small and small. So these approximation processes, you learn what's really behind them, why they work. So you have notions of continuity, differentiability, and all those things you need to understand. Convergence. So this is in your first year. You spend a lot of time learning the language of mathematics. So you can read formulas like that, and I showed you earlier, I showed you some horrendous formula. So you'll be able to read them and know what it means, more or less, even if you don't know the context. You will have to learn a bit of geometry, a bit of applied maths, probability statistics, get all the foundations. And that's your first year. You have 8 courses or 6 courses, depending on the university, how many courses you do. And in most places also, in year 2, you have to, you're still not there. yet of the results. You need a little bit more, so between 20 and 40% will be fixed. But in your second year, you can start choosing it. After first year, you know, do you like applied maths a little bit more, statistics a bit more, do you like the algebra side more, the calculus side more? By that time, you'll know a little bit. And you start specializing in 1 or 2 areas. And it will probably change. So when I was in year 1, I was all gung-ho about analysis. That was my subject. I thought, wow, this is great. In the middle of year 2, and I even thought theoretical physics is great. And I still think it is. But by the end of year 2, or mid-year 2, I suddenly decided, I sort of found out that actually algebra is what I'm good at, what I enjoy. So you will change your mind, almost certainly. And talking to my colleagues, talking to our students in their 3rd year, they all say, oh, I thought I liked that at the beginning. And then I turned out to like something completely different. It's exciting. And you get this chance, to explore everything in year 1, a little bit in year 2, in year 3, you can usually just decide, this is it, this is what I want to do, what I want to specialize in. 10 minutes, okay. Now, I want to tell you a bit about topology. So let's do that. So here, you can even laugh after 4th year. So what are the areas? Yeah, so we have mathematical methods, that's your 1st year, you learn this. You have the abstract pure mathematics, the applications, and then physical applications, physics, biology, population dynamics, whatever. Statistics, of course, discrete and algorithmic maths. And then you can do economics and finance. A lot of people go into that, or computing. And mathematical methods, I said already, vectors, complex numbers, calculus, discrete maths. All these things you will learn in the 1st year. And pure mathematics, there are very, very many areas. So the first one, Nucinkis fields, is what falls into algebra, vector spaces as well. There's analysis, complex variable fields into that, falls into that field a little bit. And then topology and geometry kind of grow out both of analysis and algebra. And then there, of course, is what some people call the queen of maths, number theory. And here is one area of pure mathematics is topology. What is that? This is the sort of the science of the shape of spaces. So what we know is our 3-dimensional space. And then you want to understand, okay, so what 2-dimensional space, black, white, what other spaces are there that sort of look around the small place, like that white bit? If you think about Columbus, yeah? Well, everybody thought the Earth was flat, because our small local experience was that we lived on a square. And then what spaces are there that sort of around us look like a square, but are globally something different? For example, a sphere. Yeah, that's what Columbus sort of realized, oh, we live on a sphere. And then as a mathematician you think, what other possibilities are there? Here's another one. It's a donut. Yeah? If you look closely, it looks like a sphere, like you live on a square. And then you say, okay, so are the donut and the sphere the same? No. Because you can't continuously deform one into the other. So you have to say, what does continuously deform something means? And in a sort of naive way, it's you don't punch holes, you don't glue. But the donut and the teacup are the same. And here you see it. You don't punch holes, you don't rip, you don't glue. All you do is you continuously deform it. The difficulty is writing down the map. Yeah? That is very difficult. So you can wave your arms about and say, okay, that's obvious, isn't it? But you have to write down the map, showing that your cup is the same as a donut. So some people say a topologist is someone who can't tell the difference between a cup and a donut. So that's us. And then you say, okay, how many more? these creatures there. And in 2 dimension it's done. That would be a third year project. It's something you can do after 2 years of mathematics, 2.5 years. In 3 dimensions, that leads us to, I don't know if you've heard about the Poincaré conjecture, about how 3-dimensional things look. So this is hugely difficult and has just recently been proved. It's one of those 1 million problems you might have heard. So, then there's of course Fermat's last theorem. Very easy to state. For n not equal to, or for n bigger than 2, there are no integers x, y, and z that satisfy this. And for 2 you have 4, 3, and 5. There you go. And for 2 you have z. And the proof is, so this is the most easy theorem to state. But it takes about 1,000 pages to prove it. And the donut's back. What the people who proved this did, they looked at curves on a donut and somehow encoded the number theory. So here is topology turning up in something number theoretic. Then you have the real world applications. Quantum theory, relativity, all the physicists will now say yay. And finance. So we have some finance. And why do we need mathematics to understand real-world applications? Look at these 2 functions. You have a blue function and an orange function. They start out the same. But then, even though there's only a tiny bit perturbed one from the other, after a while they're wildly different. So this is chaotic behavior. This is why we can't predict the weather, except for a very small one. And that's why we can't predict markets, financial mathematics. So there's a lot of applied mathematics behind this. And here, I said I'm going to write you down a wonderful formula. This formula got some people Nobel Prize in economics. It's the so-called Black-Scholes equation. And this is something that describes pricing of options. Again, so that this is this chaotic market. Prices behave randomly, and you have to describe this. And to derive to this formula, you need linear algebra, you need probability theory, and you need calculus, very heavy-duty calculus. And if you play around with this formula, what you get is a so-called heat equation. And the heat equation is something that models the movement of heat in metal rods. That's engineering, that's physics. And it's the same formula. Once you play around with it a little bit, it takes 10 minutes. You have the heat equation, and then you do the same mathematics, whether you model the heat in a rod or you model the markets. You do the same mathematics to derive at an answer. You just solve stochastic differential equations. Nothing else. Same mathematics behind some very different things. So I think that's quite amazing. Baffles me every time. There's of course statistics and probability, and there's some financial maths there, so you need statistics about how financial assets move, forecasting, weather, population forecasting, all sorts of things. This is sociology, and then discrete methods. That leads often into computing, cipher systems, cryptography, and so on. So discrete methods are so good. You draw your graphs of things that happen in a network, for example. Do we have any other? So, and then of course, cipher systems is a very important thing, and it needs discrete mathematics, but it also needs algebra. There's an area called field theory, which underpins a lot of this cryptography. Why do these things work? Why can Alice and Bob transmit data without an eavesdropper listening, or making it difficult for an eavesdropper to decode? What's behind it is algebra. Very deep mathematics. Or you can become a teacher. Yeah, I should tell you what you can become afterwards. So I tell you all the things you can do once you could see movements into finance, into further maths, into physics, into computing. And you can also become a teacher. Stand on the other side. What these two people do. And the 3. And there are a lot of universities offer this. Have a look if you're interested in that, whether they offer it. It's a scheme where you work in school for a minute, for a minute. So how do you spend your time? You go to lectures. Holloway is rather, this is a smaller university, so we have maximum 150. In your third year, you've got 20 people in each lecture. You have workshops where you work on solutions. You have tutorials where you work with one member of staff in a group of 6 or 7, which is very daunting, but it's not, because you sort of get to know each other. So you work together rather than you have this teacher standing in front of you telling you what to do. You work out problems together. I really enjoy doing tutorials because you get to know the students. And yeah, you have to go through your notes. It won't happen that you just soak it all in and it's there. You have to do some revision. And you have everything online as everywhere now. Yeah, okay, so that's what happens in most places. You have 12 lectures. That's 4 courses a term. You have some tutorials, workshops where you go over your exercises. Exercise classes where you get taught how to do it, so it's a post-mortem, where the most common mistakes, things like that. And yeah, and that's for each of the courses you will get weekly problem sheets, just like now. Very important. Yeah, that's what you have to do. It's up to you. You have to work. Yeah. Usually start with office hours, so they're not that scary, I think. I hope. And that's again, that's in most places the same thing. Coursework, you should get answers. You should ask, why did I do this wrong? Yeah, it should be on your coursework. And if not, you can ask in office hours and things like that. And yeah, most courses, there are exams in May. That's Holloway. Some people have 2 exams sessions, we have 1. And you have some projects, things like that. So you have to do a little bit of coursework and projects during the term, but it's mainly exams. Working, thinking on your feet, answering questions. And yeah, so that's 4 students at the end of their exams. They look happy. And here they look even happier. That's what it's all about. And graduation's a great day. You sort of sit with your students, you have a little party, it's in the summer. It's great, and everybody's happy. Something to look forward to. Also as an actor. Okay. Entry requirements, we talked about that earlier. Further math A-level is always helpful. It's always absolutely helpful. But in some places, if you don't have further math A-level, don't worry. After 1 year, you don't see the difference anymore. But it's, for the first year, it's absolutely helpful. And I would recommend anybody, if you have the time and the capacity, do further maths. Because it also tells you, do I like maths or not? Is it worth doing this course? And if you have other questions, yes. So these are sort of some questions you can ask yourself, but I'm out of time. What should I put in your personal statement? What do we look for? We want to see that you are excited about mathematics. Make us believe that maths is what you like. Because we enjoy it, we want to teach people who enjoy it. So make us believe that that's really, it's your choice, you want to do it. And yeah, what I try to remember. Okay. And when it's all over, you get a job somewhere. It's very likely that you get a job somewhere. You know, as I said, you're somebody who can think logically, focus on something important. They know they can throw at you a very, very difficult problem, your employers, and you'll be able to get to the core of it. Yeah. So they know that you're quite doable as a mathematician. You can survive a lot after you've survived it. So a lot of finance, a lot of computing, a lot do some more postgrad before they decide what they want to do. It's actually quite a large number of students.
So I should 13 minutes ago. Unless there is any question.
Yeah, I'm also done. So that's careers here. You can do anything when you begin. Anything. And so these were often the students who did maths and music. We have one student who now works for Formula One, and she designs Formula One racing cars.